Alright, now we're going to move on to 2.6, which deals with transformations. Transformations. In some books, or let's say if you looking for other videos to be more helpful, they also call them translations. So either one's fine. Some people like to use transformations, other people would like to say translations. And what we're going to be doing is looking at the functions. So now we've talked about function notation and identifying a function, identifying its domain. And the functions that we've looked at are absolute value, a quadratic with a parabola. We have the square root. We've also looked at a cube. And then if you guys did the quiz, if you graphed a cube root, it looks like this. So this is an absolute value. This is x squared. This is square root of x. This is x cubed. And this is a cube root. So that means there's going to be a 3 in that wedge. Cube root of x. So what we're going to be doing with these graphs is just shifting them around, stretching them, pulling them, reflecting them. We're going to be doing all those transformations or translations on these graphs. And I like to go in a very particular order, because if you sort of skip steps or try doing one transformation before another, sometimes it causes you to do it incorrectly. So I rather just sort of follow these steps. And this is the order that I'm going to teach it to you. And this is the order that we're going to be doing our translations. And I always like going with this idea of inside out. That's what I call it. Inside out. Or just to make it cool, we'll just call it in and out. Whatever, I'll just inside out. Inside and out. Or in and out for short. Maybe you remember in and out. And the idea of what I mean by in and out is because things are going to look like they're inside the function, and then I'm going to describe it as being outside of the function. And you're going to hear me say that back and forth, inside, outside the function. But the idea is, I guess another note is that we're going to be closer to x, getting further away from x. So we start, so I'm going to put a note here. Start next to x. And what I mean by starting next to x, when we're talking about function notation, that parentheses with that x, that's x is going to be on the inside. How you can see this x inside these parentheses, in some of these functions, x is inside absolute value, inside the square root, inside the cube root. It doesn't look necessarily inside x squared or x cubed, but we're going to be looking at some transformations that you will see how it's inside. So it's going to make more sense when we do an example. But one of the very first transformations that we're going to look at happens inside of the function. And these two, I'm going to put these side by side with each other. One of them is, they call it like stretch and shrink. So that's what I'm going to call it. I'm going to call it stretch and shrink. Stretch, shrink. But it's also, stretch and shrink go together. So I'm going to do the other one in a different color so we can tell the difference. So there's stretch, shrink, and there's also a reflection. So stretch, shrink, and then reflect. So these go together. So these two, this happens, like I said, inside of the function. Where this is also happening, oops, let me do it in that other color. This is also happening inside the function. And again, right next to x. But this is a negative instead of here. That c represents a constant. So you can write that somewhere if you want. Maybe I'll put a note here. C is a constant. So just a number. So a fixed number that's going to be there. And this does a stretch and shrink. This does a reflection. And what's happening is to the x. So imagine we're looking at one of these functions, any of these three. When what this reflection does, I don't know if I'm gonna have enough room, I'm gonna have to get another sheet of paper. What this reflection does here, it does a reflection. It reflects on y-axis. We're going to do some examples and you're going to see what I mean. But what's literally happening, it's just taking the x-coordinates and multiplying them by a negative. So that's the reason why it makes this reflection on the y-axis. For example, really quick on this one, what it would look like, it would take all these x's and move them to the negative side. So it would look like on one part that it did this, and then on the bottom part it takes, if you multiply the negatives times the negative, that just makes them positive. So it looks like it did this. It flipped this one over to the left hand side, but it switches the bottom to the right hand side. Similarly, the cube would do the same thing. The x's that are on the positive will end up just going to the negative, and the x's on the negative just end up going to the positive. So I'll leave that there for now, but same thing with the square root of x. That's what I mean by the reflection. It looks like a reflection on y, because it takes everything on the right hand side and you almost fold on the y-axis, and it's sort of whatever side is here, it paints it onto the other. So imagine this was paint and you took this and you folded it and then you squished it. That's what you would end up with. And then this is what you would end up with on the right hand side. Similarly with the x cubed, if you fold it, again, the idea is you're folding it and then it's going to line up together. That's what we're doing. That's what I mean by a reflection on the y-axis, because it's happening on the y. But what's really happening is the x-coordinates all being converted to a negative. So that's the reason why it looks like a reflection, because the positives are perfectly on the right and the negatives are perfectly on the left. So they end up doing this switch, move one to the other side like this. Hopefully you guys can see that. So that switch is happening. So, and it's happening to the x-coordinate. We're going to look at some examples where you can actually see the point, how the point is being changed. A big thing about these is that we're going to be mainly looking at sketches. So we learned how to graph all these functions when we were using our table. We learned how to graph them using the x and y table, but now since we're dealing with function notation, it would be the x and f of x table, because the f of x stands for y. Sorry there, I lost my train of thought, but the idea is that I don't want to use a table because you would need so many different points. Again, these aren't just lines. For lines, we're able to just get 2 points and then we're done, or use a slope-intercept form. But if we're trying to use a table on these, especially like a cube root or a square root of cube, you would need so many points to be able to see exactly where the graph is. So one thing that we're going to be doing mainly is we're going to be doing a sketch. It's not going to be a precise graph. We might have one precise point, and I'm not going to require it, but I am going to show you how that point moves along the graph as we're transforming it or translating the function. But I only want a sketch. Like here, I did a rough sketch of this reflection, and that's what I want. You have to be able to recognize what function we're looking at, and then I want you to do a rough sketch about it. Not because if I ask you to graph, you can just graph a bunch of points and then you'll have your graph. The idea for me here is just understanding how the function is behaving and what the translations are doing to it. And I'll show you, if you want to be more precise, I can show you with a couple points that we know, and we can follow those points along the translation. But now, sometimes these are combined together. You might have a negative constant in front of that x, so you not only have to take care of the negative reflection, but you're also gonna have to take care of that stretch or shrink. Something else that's important to note: everything that's inside behaves opposite of what you think it should do. In this case, you can think that maybe the negative, if it's a reflection, you would think, oh, I should do a reflection on the x, but it doesn't. It actually reflects on the y. But the idea is mainly with this stretch or shrinking that's happening. So which ones we're looking at? This constant, there's two situations. There's one situation, so I'm going to put, let's say A. One situation is when this constant is bigger than 1. And then when this constant is in between 0 and 1. That makes the world of a difference. And everything here is happening horizontally. So on the x-axis. So whatever, just imagine all the x coordinates, and those are the ones that we're affecting here. The ones that are changing are all the x coordinates. I'm not worried about the y right now. But normally, this is what I mean by things inside of the function work opposite of what you think they should. Because if you're ever multiplying a number by bigger than 1, you multiply anything by any number bigger than 1. Let's say you have $1,000 in your bank account. You multiply it by 5. That's only going to make it bigger. Whenever you're multiplying by a number bigger than 1, it's always going to make... Because when you multiply by 1, it keeps it exactly the same. Anything more than 1 is just making it bigger. Normally, you would think that's how it works. If I'm going to multiply by 5, whatever I multiply 5 by, I'm just going to make it bigger. But this is what I mean by it works opposite, because this is actually going to do a horizontal shrink. So I'm going to put it here. I'm going to put horizontal, and I'm going to put SH for shrink. Where if you multiply between 0 and 1, so that means if you multiply something by a fraction, you would think that the fraction, oops, sorry for that noise. You would think the fraction is going to make it smaller. But what it's actually doing is going to stretch it instead of shrinking it. So this is what I mean by it's working backwards. And it's going to be a horizontal stretch. I'm going to put ST instead of, so this is SH, this is ST. So think about these graphs. Imagine if this was some type of rubber band or stick. So what I mean by shrink or stretch horizontally is that you're going to compress it. So imagine you looked at this graph and you're compressing it. If I compress this in one direction, it's going to bulge upward. Similarly, if I push this one, it's also going to make it bulge. Again, this doesn't move it around. This is just sort of squishing it down towards the origin. So this is what would happen if you squish it downward. Same thing with this one. Imagine you take this and then you squish this. You're going to push this one closer to the y-axis, so it's going to look like this. You're going to also push this one closer to the y-axis, which is going to end up making it sort of narrow out. Like the more you squeeze it, the more it wants to become almost a straight line. Same thing can happen with the square root. Just imagine there's nothing on this side, but imagine this side getting squished in. Think what would happen. Now just look at, if you're looking at a parabola, if you squeeze it down, here's a parabola, and then you squish it on both sides, you're compressing it. Same thing with absolute value. So that's what I mean by what would happen if you multiply by a number bigger than 1. It's actually going to do a horizontal shrink instead of a stretch. And if you want to know precisely what is it doing to each single coordinate, so again, since this is opposite, C in this case, if it's bigger than 1, it's multiplying to x. So that means you're actually going to divide the x coordinate of your original one to be able to know where your next point is going to be. Or this is what I mean by a rough sketch. I'm like roughly sketching them to give me an idea what it's going to look. And now, like I said, for in between 0 and 1, you would think if you're multiplying something by a half, or by a fifth, by a third, it's always going to get smaller. But what this is doing is a horizontal stretch. So imagine you're taking these and you're pulling on them. Imagine this was a rope and I'm going to pull on it really hard on this side and pull it on that side. You can only imagine what's happening to this curve. And maybe you see it already. Again, if I'm pulling it, what's happening is this is actually going more down. So is this one. Because when you pull this in each direction, you're almost straightening out that function. Oops, lost that one. So that's what I mean by a horizontal stretch. Just grabbing something from both sides and then you're pulling on them, opening it apart. Think about what would that do to these other functions if you're pulling them apart. And what's happening, again, when you're multiplying by a half, that's the same thing as dividing by 2. So since if these are dividing, the opposite of that would be multiplication. And again, it's going to make more sense when we look at an example right now, what I mean by multiplication. But that's the first step. The first step is being right next to x. And then determining if you're going to either be a horizontal stretch, horizontal shrink, or if it's going to be a reflection on the y-axis. And normally here, there's sort of an intermittent step that if there is something multiplying to the x, you want to factor it out before you continue with more of your transformations, because that number is not only throwing off the x, it's going to be throwing off everything that's inside if you don't factor properly. But I'm not going to focus too much on those. I would probably put a little star on, let's say, like a 1a, which would be factor C or the negative. We won't see too many of those, but that's something you'd want to do first before you continue to the next step. And that next step, I'm going to have to use another paper, but that next step has to do with horizontal, I always feel like it's horizontal shifting. So what I mean by that is that instead of something being squished or compressed or pulled on, it's literally going to be looking exactly the same way it is, and it's going to move left or right. Left or right. That's it. That's why I said horizontal shifting. Left or right. That's all that's happening. It's either going to move left or it's going to move right. That's it. There's nothing else. But since these are inside, these are going to be inside the function. they're going to behave, and there is no two of them in this case. There's only one type. So it's going to look, let me write it down. It's going to look like x plus or minus c. What I mean by plus or minus is that you can either add or subtract inside of the function. So again, it will look, for example, it might look like the square root of x minus 2. And that's what I mean by being inside those parentheses. I mean, inside of something. For the x squared, there might be an example that has x minus 2, all in parentheses square. This square is what's telling us that it's a parabola, but there can be a lot of other things going on. Let me put a little arrow there. So we can still shift this around, so on and so forth. But, like I said, they behave opposite of what you think they should be doing. If this is a horizontal shift, this is moving left to right. That part is not being tricky. The tricky part is knowing if you're either going to go left or right. Again, like I said, if it's things about inside, it's always going to work opposite of what you think you should be doing. So what I mean by that is if it's positive, you're actually going to move it to the left. Whereas if it's negative, you're actually going to move to the right. You're going to move the function, not like anything else. It's just the function's going to move left to right. But if it's positive, you move it to the left. If it's negative, you move to the right. Again, because it's doing opposite of what you think it should be doing. So instead of adding to mean you're going to the right, you would subtract to go. I mean, if you're adding, you have to go to the left. If you're subtracting, you have to go to the right. And again, intuitively, you would think positive means right and negative means left. But this is what I mean by horizontal shifts work backwards to what you think they should be doing. So that's the main thing about horizontal shifting. Just make sure you watch out for if it's inside or outside and those negatives, because you might get confused seeing all these different videos and stuff. So you want to make sure you're focusing on this. So the horizontal shift. Let's continue with the other couple steps for these translations. Remember, what's inside works opposite of what you think it should do. So if it's positive, it will go left instead of right. If it's negative, it actually goes right instead of left. And we'll see that in a few examples. But now, so let's switch it. Here we have, so I'm just going to rewrite them again. So the first was if there's a constant multiplying or a negative, and don't forget that constant could either be bigger than 1 or in between 0 and 1. And sometimes you have to factor out. I'm going to put it in here. Sometimes you have to factor. We're not going to do this too much, but I'd rather have it here. Sometimes you can factor out the C and the negative. But if we don't see that, that's fine. And then we talked about the shifting. This shifts it horizontally left or right, where this does a stretch or shrink and this does a reflection. Now the third one that I want to look at is, again, we're working from inside out. Let's not forget that, from inside and out. So now we're going to go to, we started with multiplying to x and then adding to x, and then we're going to get to the outside of these parentheses now. So we're not inside anymore. We're going to go out, and we're going to have some sort of this step again, but now it's happening on the outside, or it might be a negative on the outside. And this is, don't forget, your function, this represents y. So what's happening now is we're doing everything to the y coordinate of our function. We'll see, so we'll follow some points on some of these examples so we can see exactly what's happening. So, but same as the first ones, you can multiply by something that's bigger than 1, or you can multiply by a constant that's in between 0 and 1. So these are the two cases here, same as before. But everything outside behaves the way you think it's supposed to. So what I mean by that is, if you multiply by a number bigger than 1, it's actually going to do a vertical stretch. So I'm going to put ST. Or if you multiply, it's going to be a vertical shrink. So by stretch or shrink is now, if you're looking at a function on the y-axis, you're going to pull on it. For example, let's say if we're looking at the absolute value. So a stretch would be, imagine you grab this point and you pull. Let's say if you were to pull on the legs up, then it's going to do something like this. Whereas if you compress it downward, it's just going to open it much wider. So that's a vertical stretch or vertical shrink. Like it's compressing it. Stretching is like it's pulling it. So that's the two different things that can happen. And we're going to see some more examples of each type of stretch and shrink. And then I'm going to go to just some of these steps are all going to be in one. Now, this is for the negative, this is just a reflection. This is a reflection on, the other one was this was a reflection on the x-axis. This is a reflection this was a reflection on the y. This one's going to be a reflection on the x-axis. So that means that if we're looking at the absolute value, what would happen, it would reflect everything that's above, below. If it's below, it's going to shift it above, but it does a reflection on the x-axis. If you see that negative outside. And then we get to the last step, which is the most outer part of it. And that's adding and subtracting by a constant. And again, everything outside behaves the way it's supposed to. Everything inside behaves opposite of what's supposed to. So in this case, when we talk about a positive, that actually moves it up. So it shifts it vertically. Where if you see a negative, that actually moves it down. And see, this is how you can see the split off point between the inside and outside that I'm talking about. These are inside, these are outside. And there's the same thing. There's a multiplication and there's addition. There's a multiplication and addition, and then there's the negative, and here's the negative product. But it happens inside and it happens outside. And we work our way from inside and out. But I want to look at some examples of this. I don't want to so you don't just look at it in general. Let's see if we can do some examples of these. So for instance, let me pull up the square the square root function. So when we graph the square root function, so let's say we have, so the one thing that I sort of left out here is the zero step. What we call this, we have to be able to identify. I'm going to try to squeeze it up here. Identify. Some like to call it the parent function, the general function. Different books call them different things. What I mean by that is because it can ask you to sketch. And let's say we start with, we're sketching g of x equal to the square root of 2x. So what we need to do first is step 0, which is we have to be able to identify the parent function. What I mean by that is we have to see which one of these functions are we dealing with. So we already have a rough, because we're not going to do a table. We're just going to graph it. We can make our x and g of x table, and then just plug in a bunch of x values and find the corresponding y and then graph it. What this helps us do is get a rough idea of what this function is doing, and that way we can do a rough sketch. So first, I have to identify that the parent function in this is the square root function. So I know the square root function looks like this. And there's some specific points that we do know. For example, we know that this is 1, 1. We also have another point further along at 1 and at 4. So right here we have, this is 4, 2. Just so you can see a little bit of what's happening to this graph. I probably should have made it bigger, and I'll show you after. But so now my next step is to work from inside and out. So the first thing I see, there's something multiplying to this x. So what we're going to be focusing on in this situation, we're going to be focusing on these x coordinates here, because that's how it's manipulating them. It's manipulating those x coordinates. And the way it's manipulating them is, remember, if you multiply by a constant that's bigger than 1, it's actually going to do a horizontal shrink. So what that means, it's going to take this graph and you're going to compress it. And as you compress it, it's going to force it to do something like this. It's going to look like it goes higher because it's being compressed downward. And that's what I mean by a horizontal shrink, because this number is bigger than 2. It's going to shrink it horizontally. But then maybe we want to know what's happening to these points that I labeled. So let me call one A and then this one B. Maybe you want to know what's happening to the points exactly. Like, why is it doing this shrink? And like I said, everything behaves opposite of what you think it should do. So this isn't multiplying the x. I mean, yes, if you plug in a 4, it multiplies it by 2. But what's happening to this particular point is you're actually dividing this value by 2. And you're also dividing this one by 2. Well, that ends up happening. If I divide 4 by 2, that means my new point, my new b, 4 divided by 2 is 2, but nothing's happening to my y, while my y is staying in the exact same place. So this got shifted because it's being compressed. So imagine you pushed it. Again, you're not changing any of the y values. It's all the x values are sort of getting squished downward. And same thing here. This used to be a 1. But if I divide that 1 by 2, then I'm left with a 1/2. And now my point gets shifted over. I know it's hard to see there. So I'm going to show you on Desmos. So I'm going to pull up my laptop. And hopefully we can see it. Let me set it up. Alright, so what we're going to look at is focus on that one point. So let's say we're looking at g of x. So again, we're stating that the parent function is x. Oops. Put x here. Okay. So here it is. This is what a square root looks like. So again, the points that we do know, and I'm highlight here. So the one I was talking, we don't have to worry about so many points. Again, because this is just supposed to be a rough sketch. We're not supposed to be looking at a million different points. So here are the 2 points that I was referencing on my paper. So what's happening when I put that 2 right here, it's going to compress this. It's going to compress all the x values. And you're going to see how it does that. So now I'm going to make another function, but now this is going to have the 2x. So 2, and then you're going to see how everything is being compressed. Being compressed downward. And as this number, like I said, as the number gets bigger, I'm going to put a couple. As the number gets bigger, so again, it's only compressing it more and more and more. And you can see that's getting compressed more. Even though it looks like this is going upward, what's happening is these are getting pushed over. So if these get pushed over, that's what forces this to go higher up. If they get pushed more, they go higher up, and they get pushed more, this ends up having to go higher and higher. So we're just going to look at what happened to these 2 points. And of course, the higher this gets, the bigger it's going to do. But when it's in between, so I'm going to delete this one. But how we talked about being in between 0 and 1. So I'm going to pull that out right here. Whoops. So when it's in between 0 and 1, it's actually a horizontal stretch. So you're going to see all these points getting pulled in this direction. So I'm going to put 1/2 in here, and you can see that. It's getting pulled in that direction. Let me put 1/3, and you can see how all these points, it's these same points here, they're all going to, like you're grabbing it and you're just pulling it. Like if it was a rubber band, you're pulling on it, and it's only getting, like it almost wants to become like a straight line. Like imagine I put 1/25. So you see, that's like extremely pulling on it horizontally. But now let's focus on what's happening to these 2 points. Again, that's just a rough sketch, like how I made. I can stretch it and shrink it vertically, horizontally, but we want to see what's actually happening. And like I said, we're not multiplying this value here by 1. What this ends up happening is we're taking this 2 and we're dividing that x coordinate because it's opposite. Because it's multiplying the x. So what's going to happen in here is we're going to divide. So that point, we divide that 1 by 1/2. So that point becomes 1 and 1/2. And you can see how it's getting shifted over if you were to push it. Same thing with this one. We have 4, 2. So the x coordinate, what we're going to do, same. It's going to take this 2 and it's going to divide it. So let's look. And 4 divided by 2 is 2. And that y is still exactly the same. That's not changing whatsoever. And that's how you can see these points, they didn't shift up. They got compressed to the left. And that's how you can see they're here, but they are getting horizontally shrinking. They're being shrunk horizontally. Sorry about that. So that's what's happening here, and you can see that. Similarly, what happened is if I have with this, if this was 3x inside. So what's happening to this, these are the same points. I'm not dividing this one. It's always to the original one. Everything's based off the original. We take this original point and then we're actually dividing by 3. So now that point's at 1/3, 1. And that's how you can see it. It's that point just keeps getting pushed even more. And same with the one above. What we end up doing now, we take the 4 and divide that 4 by 3. So 4 divided by 3. And the y is still exactly the same. And you can see, I'm pushing it and then pushing it. And the bigger it gets, it's getting pushed further and further. And that's why this ends up looking like it's going higher, because you're compressing it. So it's like bulging upward. And if you multiply by something less than 1/2, it gets pulled in the other direction. So even though that wasn't the example we looked at, I can show you what's happening to the similar argument is happening to 1/2. So now instead of getting pushed this way, it's getting stretched horizontally. So this point here goes from 1 and you can see where it is. It's right here. I don't know if you can see my little dot, but it's literally in this thing. Because what's happening is, what I end up doing, I end up multiplying. So it's kind of the same thing is happening. Since this is multiplying to x, I need to do the opposite. I need to divide. The same way there was a 2 here, it divided that 1. But now we have to divide by a half. That gets a little trickier. Because if you remember algebra, and again, we're not going to focus on this too much. I just want you to see on one example what's happening to these points. And then after this, we're just doing rough sketches. So what's happening is we're taking that 1, and I'm dividing that 1 by a half. But if you remember from algebra, what you end up when you divide by a fraction, you have to multiply by the reciprocal. So what ends up happening is that 1 ends up becoming 2. And the 4, because it's the other coordinate, also divided by a half. But I end up multiplying it by 2. Oops. So that gives me 2 times 4 is 8. So if we look here, because we're going to divide this 1 here by a half. But we're going to divide it by a half, which ends up giving us 2. But the y is still the same. And then we have, whoops. I don't know why I put 2 parentheses for. Same, and then like how we did with this one. We take this 4 and divide it by a half. When you divide it by a half, you end up multiplying it by 2, which gives you 8, comma, and then the y is still exactly the same. I have to pull this out a little bit so you guys can see. Whoops. What's happening? Hold on. Okay, and there they are. You can see them. Here's that 2, comma 1. And there's that 8, comma 2. So these 2 points here, now they're getting stretched horizontally instead of being pushed horizontally. Instead of being shrunken horizontally, they're being stretched horizontally. And there's always the negative that I talked about. All the negative does is same thing. Since it's multiplied to x, we divide, but anything divided by a negative is just going to convert it to a negative. So let's say, let me go back to this 2x that we originally were looking at. And if I put a negative here, what it's doing, so again, don't forget, the points had all shifted over because I divided it by 2. And I divided this 4 by 2, which left me with 2. And then now I have to shift. You could either done the reflection and then shift it, but it's nicer to just do this. That we're going to take these values and we're going to divide it by, I'm going to put like a negative in front here. And when I put that negative in front of this 2, it's going to convert this 1/2 to a negative 1/2. So I'm already going to put the points here. It's going to convert this to a negative. And it's going to convert this to a negative. And then you're going to see these points are on this side. So when I input that negative here, these points are getting shifted over to the other side. And you're going to see that right now. Then I can turn it on and off and you can see how that reflection happens. Whatever was here, just getting reflected onto the other side because you reflect on the y-axis. But what's actually happening is just your x coordinates are becoming negative. So instead of being a 1/2, comma 1, it becomes a negative 1/2, comma 1. Instead of being 2, comma 2, it becomes negative 2, comma 2. And it just shifts over to the other side. And then we have all our points. I can click, but yeah. That's what's happening to them. So that's the example of the stretch. And this happens, you can see this in any other examples. For instance, we can do this to the absolute value. So again, now I'm just making up examples now. So yeah, we have to remember this is the parent function. It makes a perfect V because it's 1, 1, 2, 2, 3, 2, negative 1, 1, negative 2, 1. They all cross at that 1, like the slope is 1. It goes up 1, right 1, up 1, right 1, up 1, right 1, so on and so forth. But the same thing's going to happen. If I have a 2 inside of here, Control copy. Let's say I put a 2 inside. So again, everything's happening inside. It takes this point. Again, I know the points that are here. Let's say I use 2, 2. So we're going to be messing with these points here. So if I put a 2 in here, same thing. It's going to take this 1 and that 2, and it's going to divide it by 2. So if I divide this x by 2, that's just going to become a half. And if I divide this 2 by 2, that's just going to give me 1. So you can start to see how that shrink is going to happen. So when I put this 2 here, there's that horizontal shrink. So imagine you have this V and you're compressing it. That's why it looks like it's getting like more narrow, and the bigger number you multiply by, the more it's just getting compressed and compressed and compressed. In other words, it's shrinking horizontally. And you can see that as that value gets bigger, so let me put this one here. As that gets bigger, it only keeps getting compressed more, 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 and more. But that's what's happening to the actual points on your original function. You are actually taking this coefficient of x and dividing it to the x, all the x coordinates on these points. Literally, there's an infinite amount of points on this function, this original f of x. Let me close everything. So there's an infinite amount of them. And all of these here that are all along these. So all these points right here that you can see highlighting, all these x's. There's an infinite amount. That's why there's no gaps. All those x's are being divided by 2, and that's why they're shifting over. So it looks like it's being a horizontal shrink. Now, if I multiply by a half, let's say if I switch this to a half, same thing as before, I'm still dividing these x coordinates here, this 1, 1, 2, 2, but now I'm dividing it by a half. But when you're dividing it by a half, what you're doing is you end up multiplying that by the reciprocal, you actually end up multiplying. So if I multiply this 1 by 2, I'm going to have a 2 here. I'm going to multiply this 2 by 2, I'm going to have a 4. And you can see how now it's going to be a horizontal shrink. So it's going to take the V and it's going to open it up more. So let me put the 1/2 here. And when I turn the viewing on, you're going to see that it's going to get stretched open. So the same thing on this side. It's just going to look like it's stretching more. And then the bigger or the smaller, I guess, in between 0 and 1, that number gets. So let's say 1/10. You can see how much it's being stretched. The point's almost trying to be stretched to a horizontal line. And that's the very first transformation. And it's technically one of the trickier ones because it's kind of difficult to see how to follow these points. But maybe you're understanding what's happening to the graph overall. So let me pause here. And I'm going to go back to the paper so we can see a few more of these examples. So we were able to see how these are shifting. So, and that's the first thing that we did. We saw that there was that 2 multiplying to your x. Sometimes there might be multiple things happening. Or sometimes there might not be anything at all. So the next thing to look at is these. We're not going to focus on factoring. There's nothing to factor here. So we have shift this horizontal shifting. So for example, let's say, let me switch it up and have an x squared. So, we have to be able to recognize what's the parent function here. That's the first thing you want to be able to identify. And this square is helping me identify what function are we dealing with, and we're dealing with the x squared. Now, let me draw this one a little bigger so maybe I can see what's happening. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. And we know the points for a parabola. There's one at 0, 0. There's one at 1 and 1. There's one at 2 and 4. There's one at -1 and 1. There's one at -2 and 4. And that's how we get the parabola. And we roughly know what the parabola looks like already. So now, again, you still want to see if there's anything multiplying to the x. And there's nothing multiplying to the x right now. Hence, we're not going to do this. We're going to move on to the second thing. Since there's nothing multiplying, there's nothing to factor. The second thing is this +2. And like I said, everything inside is a horizontal transformation, but works opposite of what you think it should do. So remember I said when it's positive, that means it's actually shifting to the left. So normally you would think that positive is moving it to the right, but in inside, I can't emphasize this enough, it's doing opposite of what you think it should do. So again, I know some of these points. I know this is 1, 1, and I know this particular point is 2, 4. And what's happening here is that we're actually shifting this. So instead of adding by 2, what this is doing, you're going to do the opposite to the x coordinate. Same as before. In this example, this was multiplying by 2. I divided the x coordinates by this number. Here, I'm adding to the x coordinate. So on these two, I'm not going to add by 2. I'm going to actually subtract. Subtract by 2. So if I subtract this one by 2, that's going to end up giving me -1, -1, so it's going to be right here. That's this point right there, -1, 1. Whereas if I subtract this by 2, that's going to end up giving me 0, 4. And again, this is just taking the graph and shifting it over to the left, because that's what the positive does. And same thing with the origin. The origin is getting shifted over too. And then, for the sake of time, I'm just going to do a rough sketch. These, well, we know what they are exactly. But that's this idea of horizontal shift left to right. And I'm not going to focus too much on it. I just want you guys to be able to see it. I want to do an example of each one and then get into what happens when you see all these different types of transformations in one example alone. So for the next one, we have to talk about the multiplication outside. So now things are behaving the way they're supposed to. So I'm focusing on if you multiply by a number outside, it might be a negative as well. So for example, we're going to sketch the graphs again. So I think that was A, B, we're at C. Let me do f of x is equal to, let's do, I did the absolute value already. Let me do, I think I could do 2x cubed, or I did the square root. Kind of showed you guys the absolute value. We did the parabola now. Yeah, let me do the x cubed. So with the x cubed, so again, it's not inside. When I'm talking about inside, there literally either has to be a radical symbol, an absolute value symbol, or a parentheses to imply that we're actually inside. Since there's no parentheses here, then I'm not inside at all. But the first thing we should do is identify the parent function. And the parent function is x cubed, which you know what x cubed looks like. X cubed looks like this. And there's some points that we should already know for x cubed. And some of those points, I know 1, there's 0, 0, there's 1, 1, but then 2 is at 8. So it's going to be somewhere really high. I can't even draw it here. Negative 1 is going to be at 1, and then negative 2, when you cube it, it's also going to give you a negative 8. So it's going to be really low. And it's going to end up giving you this graph here. And it continues, right? It's going to continue forever. Now, we identified what the parent function is. I now want to see if anything is multiplying inside, either by negative or a positive, and there is nothing multiplying inside. Second, now I have to see if there's anything multiplying outside of the function. And in this situation, there's a 2. And we know these coordinates. This coordinate here is 1, 1, whereas this coordinate here is negative 1, 1. Oops, sorry, I shifted this over a bit. But the idea is now we're going to focus on the y coordinate instead of the x. But everything outside of the function behaves. So if you multiply by something bigger than 1, all it's going to do is just make it bigger. So what we do now is we take the y coordinates and we multiply them by 2. So this 1, 1 times 2 is going to end up being 2, 1. Because since it's bigger than 1, it's going to be a, oops, sorry, that's not it. It's going to be a vertical stretch. So that means imagine you're grabbing these two ends and you're pulling on them. You can only imagine what's going to happen as you pull. They're going to begin to straighten out. So that's not the point there. Because this 2 gets multiplied to the y coordinate. So the x is still the same, but my 2 ends up being 2. And you can see how that's going to shift this over a bit. And if we had the other coordinate that we're looking at, if we were looking at the coordinate 2, 8, you would see more. But this is the idea here. The origin is not shifting. Because if you multiply the origin by 0, it's still going to be 0. But this one is going to shift over by 2. There's going to be negative 2, and it's going to be 1, 2 here. And this would be the rough sketch. So again, this is just a rough sketch of the graph. I don't need it to be super precise. If you want to use a couple points, that's perfectly fine with me. But this is how you can see how it's a vertical stretch because it's getting pulled on it. And that's what the 2 is doing. And then you lastly go to, so again, either there's a negative outside, and then we have to oh, I skipped a step. So for 2, we're supposed to focus on if something is adding or subtracting inside. 3 is the one that we're dealing with, the constant outside or the negative outside. So if it's bigger than 1, it's going to be a vertical stretch. Where if it's in between 0 and 1, that's going to be a vertical shrink. And that's what happened here. And lastly, we're trying to see if there's any vertical transformations. So vertical transformation. You have to they also like to call it a vertical shift. So like I said, it works opposite. Here, everything outside where it works the way it's supposed to. So that's something that you're adding or subtracting outside. That doesn't affect it at all. It just moves it up or down. So that's pretty much it for the cube. That's what's happening to the points, but if you can see, it's just going to stretch it vertically. And oh, I skipped the I didn't have an example here, but if you're multiplying by negative, it would take this and then it's going to reflect on the y-axis. So keep that in mind. It's doing a, sorry, it's not on the y, it's on the x-axis. So this part is coming below. This part is also, down here is coming above. So it's tricky to see what's happening because it's the same color. But when it's outside, it does a reflection on the x-axis. Lastly, so we know what happens when you multiply inside, when you add or subtract inside, when you multiply or subtract outside. Now we have to focus on the vertical. So for 4, that's if you add or subtract outside of the function. And this is usually straightforward. So if you have a positive, it's up. You have a negative, it's down. Alright, so if we see the example, let's say I do g of x is equal to, let's do, what have we not done yet? Let me do another absolute value. I'm going to do plus 3. So again, same thing as before. Everything now is happening to the y coordinates instead of the x's. So we have to be able to identify the parent function, and then we can see the parent function here is the absolute value of x, which makes a perfect v. Again, we know some points, 1, 1, 2, 2. Those are some points on that function. So now we have to see first, is anything multiplying to x? No. Is anything adding, subtracting x? No. Is there anything multiplying to y on the outside? No. Now, is there anything adding or subtracting to the y outside? And there is, it's at 3. But like I said before, we know these coordinates here. This is 2, 2, and this is 1, 1. Now, what it does, everything's happening, because don't forget, this f of x is y. So when we're adding to outside, it behaves the way it's supposed to. So I'm going to look at these y coordinates now instead of the x's, and I'm going to add the 3 to them. So this 1, 2 is going to become 1, 5. Well, it's supposed to be 1, 1. I was like, I don't know what I wrote. And I don't know why I said 5. Oh, this is supposed to be a 1 for this point here. So 1, 1, you add by 3, that's going to give you 4. So instead of being here, it's going to be 1, 2, 3. And this one moves up also 3. So it'll be 1, 2, 3. And everything here in this case is just being shifted upward. Shifted upward. Because everything is being added to 3. So it's going to look straight up. It's going to go up 1, 2, 3. It's going to look like this. So everything is just getting shifted up by a factor of 3. So here you have to see a little bit of what all of them are doing. I'm going to switch back to the computer so you guys can see a few more examples, and it graphs them much quicker than me doing it by hand.